Think for a moment about the sheer amount of energy we use every single day. I mean, charging our phones, flipping light switches, driving to work.
Hmm.
It's this constant hum of power that, underpins modern life. And have you ever stopped to really consider where all that energy comes from?
It's something we often take for granted, isn't it?
Totally. So today we're embarking on a fascinating exploration, digging deep into a topic that might seem, well, a bit counterintuitive. Squeezing power from a stone. Energy resources.
Yeah, that chapter title really captures it perfectly. Humanity's relentless pursuit of power. And when we talk about an energy resource, we're basically identifying a material, something we can tap to get usable energy.
Right.
The chapter uses a great analogy right at the start. Think of a wolf hunting. For that wolf, mice and rabbits are its energy resource. They're the fuel that keeps it going.
That's a really good way to frame it. And for us humans, wow, our energy journey has been quite the evolution.
Oh, absolutely.
We started just like those wolves, relying only on the energy in our food. Then came fire that was huge.
A massive leap.
Suddenly, wood, even dried animal dung, became these crucial energy resources, portable fuels we could actually control. But as our societies grew, so did our energy appetites.
Exponentially, really.
We harnessed animal power, the wind, flowing water, but it still wasn't enough. You read about things like, entire forests being cleared in 17th century Europe just to fuel iron production. It really hammers home how our demands just kept escalating.
And the Industrial Revolution, well, it craved something more concentrated, something easier to transport.
Yeah.
And that's when we really turned to coal, the compressed remains of ancient plants.
And the scale of our energy appetite since then is just, it's almost hard to wrap your head around.
It really is. The chapter points out that a typical city dweller in the U.S. today uses over 110 times the energy of a prehistoric hunter-gatherer.
Wow, 110 times.
And as more nations industrialize, especially across Asia, their energy demands have just exploded. Right now in the developed world, we're mainly running on oil, natural gas, and coal. Although there's definitely a growing focus on nuclear, geothermal, solar, even biofuels.
And those recent breakthroughs in getting oil and gas out of shale rock, that's really shaken things up too, hasn't it?
Oh, dramatically.
Yeah.
It's completely reshaped the energy landscape in just the last couple of decades.
Absolutely. And that's exactly why we're doing this deep dive today. Our goal is to really unravel the geologic origins of these vital energy resources, understand their limits, because they do have limits, and look at the consequences of using them, both the good and the bad.
Right, the whole picture. We're basing our exploration on this really comprehensive chapter from Earth, Portrait of a Planet.
Okay, so what's the game plan? How are we tackling this?
Well, we'll start by looking at the fundamental sources of energy within the Earth system itself. Then we'll zero in on hydrocarbons, oil, and natural gas, getting into the geology, including those trickier unconventional sources.
Yep.
Then we'll dig into the story of coal, how it formed from ancient swamps. Nuclear power will follow that. And finally, we'll explore the whole spectrum of alternative energy options and the, complex choices we face about our energy future.
All right, sounds like a plan. Let's jump right in with those hydrocarbon resources. Oil and natural gas. They're the big players in our current energy mix, aren't they? I mean, gasoline, jet fuel, we rely so heavily on them.
We absolutely do. And a huge reason for that dominance is their incredibly high energy density.
Energy density meaning how much energy is packed into a certain amount.
Exactly. Just to give you an idea, a single gram of oil contains roughly twice the energy of a gram of coal.
Okay.
And get this 500 times more energy than a gram of a lead-acid car battery.
500 times. No wonder batteries aren't powering airplanes yet.
Precisely. That's why a plane can fly across continents on jet fuel. It'll be completely impossible with current battery tech. Chemically speaking, both oil and gas are hydrocarbons. They're organic compounds built from chains or rings of carbon and hydrogen atoms.
Hydrocarbons, like hydrogen and carbon. Makes sense.
And interestingly, these are the same basic building blocks that make up, all living things.
Right, and they show up in different forms, don't they? We see gases like propane for BBQs, liquids like gasoline for cars, and even really thick solids like tar. What makes them so different?
Yeah, exactly. The physical state gas, liquid or solid, it's mostly down to the length of those hydrocarbon chains, those molecules.
Okay.
Shorter chains tend to be less viscous, they flow easily, and more volatile, meaning they evaporate readily.
Like the propane gas.
Perfect example. Very short chains. Gasoline has intermediate length chains, and tar. That's made of extremely long, tangled chains, which makes it thick and sticky.
So we burn these hydrocarbons for energy.
Yeah.
What's actually happening when we, say, burn gasoline in an engine? What's the reaction?
It's a chemical reaction with oxygen, fundamentally the same as burning wood, just with different molecules. The hydrocarbons react with oxygen, and the outputs are carbon dioxide, water, and crucially, energy released as heat and light.
Ah, so it's releasing the energy stored in those chemical bonds.
Exactly. It's the potential energy stored between the carbon and hydrogen atoms that gets converted into a usable form. That released heat can power our cars or create the high-pressure steam that spins turbines and power plants.
Now, here's something you hear a lot. Oil and gas come from dinosaurs, or maybe giant buried forests. Our chapter clears that up, doesn't it?
It certainly does, and it's a common misconception. While the image of, T-Rex juice is kind of fun, the reality is that the hydrocarbon molecules in oil and gas primarily come from lipids, fatty molecules that were once part of plankton.
Plankton, like the tiny microscopic stuff floating in the ocean.
Exactly. Microscopic organisms, algae, protists, tiny animals floating in oceans and lakes. It's their soft, organic tissues, not their shells or anything hard, that undergo this incredible transformation over millions of years.
Wow, such tiny things having such a massive impact. Okay, so walk us through it. How do these microscopic bits of life turn into the oil and gas that, well, runs our world?
It's quite a journey, and it takes a very long time. First, when these plankton die, they drift down and settle on the floors of quiet lakes or seas.
Quiet water, okay.
Right, calm conditions are important so they can accumulate. Now, normally, a lot of this organic stuff would just get eaten by other organisms on the way down or on the seafloor.
Makes sense.
But if the surface waters are really productive, lots of nutrients, lots of sunlight leading to big plankton blooms, then a significant amount can die and sink relatively quickly. And here's the absolutely crucial part. The bottom water needs to be oxygen poor, or anoxic.
Why is the lack of oxygen so important?
Because in oxygen-rich environments, microbes and scavengers would just decompose and consume almost all that dead plankton before it has a chance to get buried. Low oxygen preserves it.
Got it. Anoxic conditions are key. So what happens next to this preserved organic goo on the seafloor?
Well, in these oxygen-poor spots, the decaying organic material mixes with fine sediments like clay particles, forming this organic, rich, muddy ooze. As more and more sediment layers pile up on top over time, this ooze gets buried deeper and deeper. The weight squeezes out the water, and it gets compacted. Eventually, this organic, rich mud lithifies it, turns into rock, becoming what we call black organic shale.
Black shale. And that's the source rock.
That is the source rock. It contains the raw ingredients for hydrocarbons. Now, if this source rock gets buried even deeper, let's say between roughly 2 and 4 kilometers down.
That's pretty deep.
It is. Down there, the temperature starts to climb because of the Earth's natural geothermal gradient. It just gets hotter the deeper you go. These higher temperatures trigger slow chemical reactions that gradually transform the complex organic molecules into a waxy substance called kerogen.
Kerogen, okay.
And shale rock that contains a lot of this kerogen is often called oil shale.
So we've got kerogen trapped in the source rock. How does that turn into the actual liquid oil and natural gas we use?
Good question. If that oil shale gets buried even deeper and gets hotter, specifically exceeding about 90 degrees Celsius or roughly 200 Fahrenheit.
Okay, hotter still.
Right. Those big complex kerogen molecules start to break down. They crack into smaller, simpler molecules. And those are the oil and natural gas molecules.
Oh, okay.
Interestingly, there's a specific temperature range, often called the oil window, typically between about 90 and 160 degrees Celsius, where oil generation happens and the oil can remain relatively stable.
The oil window, so like a sweet spot for temperature.
Exactly. If the temperature climbs much higher, say above 160 C, any remaining oil tends to break down further into natural gas. We call that the gas window.
And if it gets even hotter than that?
If it gets really hot, above maybe 225 Celsius or so, almost all the hydrogen gets driven off, and you're pretty much left with graphite, which is just pure carbon.
Wow.
So oil formation really needs that relatively narrow temperature window. Generally, that corresponds to depths between about 3.5 and 6.5 kilometers, or roughly 2 to 4 miles, assuming a typical geothermal gradient. Natural gas, being more stable at higher temperatures, can form and survive deeper, maybe down to 9 kilometers or so.
That's fascinating. It explains why we find this stuff in the upper crust, not super deep. Now, the chapter also talks about conventional versus unconventional reserves. What's the main difference there?
Yeah, that's a really important distinction today. It basically boils down to how easy and therefore how economical it is to get the oil or gas out.
Okay.
Conventional reserves are where the oil and gas can flow pretty freely through the porous rock they're in, right into a drilled well. You can basically pump it out relatively easily.
Like sucking liquid through a normal straw?
Good analogy. Unconventional reserves, on the other hand, hold significant amounts of hydrocarbons, but the rock itself might have very low permeability, meaning fluids can't flow through it easily, or the hydrocarbons themselves might be super thick and viscous, almost like molasses.
So like trying to suck that thick milkshake through a tiny coffee stir.
Exactly. That's a perfect way to think about it.
Yeah.
Extracting unconventional reserves often requires new, more complex, and usually more expensive technologies to basically force the hydrocarbons out.
Makes sense. Okay, so let's dig into those conventional systems first. What are the essential geological ingredients you need for one to form and actually hold oil or gas that we can extract?
Right. For a conventional hydrocarbon system to work, you need a very specific sequence of geological events and conditions to all line up perfectly. It's quite demanding.
Like a geological recipe.
Kind of, yeah. We've already talked about the first two key ingredients. First, you need that organic-rich source rock to form.
The black shale with the plankton remains?
Correct. Second, you need the right temperature conditions over millions of years, that oil or gas window, to transform the organic matter into hydrocarbons.
Got it. Source rock and heat. What else?
The next crucial step is migration. The oil and gas generated in the source rock, which is usually quite impermeable, have to be able to move out of it and into a different rock layer that is permeable, the reservoir rock.
Okay, migration into a reservoir rock, and then?
And finally, those migrating hydrocarbons need to be trapped. They need to accumulate in a specific geological structure, what we call an oil trap, that prevents them from just escaping all the way to the surface.
So, source rock, heat, migration, reservoir rock, and a trap. That's the sequence.
That's the classic conventional system, yes.
Let's talk about that reservoir rock. You said it needs to be permeable. What makes a rock a good reservoir?
A good reservoir rock needs two key properties: porosity and permeability.
Porosity and permeability.
Porosity is basically the amount of empty space within the rock. Think of it like the holes in a sponge. These spaces can be tiny pores between mineral grains or larger cracks and fractures. That's where the oil and gas actually reside.
Right.
Permeability, on the other hand, is about how well those pores and cracks are connected. It measures how easily fluids, like oil and gas, can flow through the rock along those interconnected pathways.
Ah, so you can have lots of holes, high porosity, but if they aren't connected, the fluid can't move, low permeability.
Exactly, you've got it. High porosity doesn't guarantee high permeability. A good reservoir needs both enough space to hold the hydrocarbons and good connections between those spaces, so the hydrocarbons can flow towards a well when you drill into it.
So what kinds of rocks usually make good reservoirs?
Well, poorly cemented sandstone is a classic example. The spaces between the sand grains provide both good porosity and good permeability.
Okay.
Highly fractured rocks can also be great reservoirs, even if the rock matrix itself isn't very porous. The network of cracks creates the pathways for fluid flow.
Like fractured limestone.
Precisely. Some limestones can become very good reservoirs if groundwater has dissolved channels and pathways through them along existing cracks or bedding planes. Generally, the higher the porosity, the more oil and gas the rock can hold. And the higher the permeability, the easier and cheaper it is to get it out.
Okay, so the oil and gas form in the source rock, which isn't very permeable. How do they actually get out of that source rock and into the permeable reservoir rock next door, so to speak?
That's the migration process. And the main driving force is buoyancy.
Buoyancy. Because they're lighter than water.
Exactly. Both oil and natural gas are significantly less dense than the salty groundwater, or brine, that usually fills the pore spaces in rocks deep underground. Think of oil and vinegar in salad dressing. The oil naturally floats to the top.
Right.
Same principle here. Natural gas is even lighter than oil, so it will try to get above any oil. This upward buoyant force pushes the generated hydrocarbons out of the relatively tight source rock, likely squeezing through tiny fractures or interconnected pore throats, into any overlying permeable pathways, maybe fractures, maybe a more porous rock layer that lead towards a potential reservoir rock.
And this isn't a fast process, I imagine.
Not at all. This migration can be incredibly slow, taking thousands, even millions of years for the hydrocarbons to travel significant distances.
Okay, so the oil and gas have slowly migrated into this porous and permeable reservoir rock. But you said they need to be trapped there. What does the trap actually do?
The trap is absolutely essential. Without a trap, Those buoyant hydrocarbons would just keep migrating upwards through the reservoir rock, following permeable paths, and eventually they could reach the Earth's surface as an oil or gas seep.
Ah, so they just leak out.
Pretty much, yes. A geological trap is a specific underground arrangement of rock layers that stops this upward movement and forces the oil and gas to accumulate in a confined area within the reservoir rock.
What makes up a trap?
It needs two key components. First, you need a seal rock, or cap rock. This is a layer of rock above the reservoir rock that is relatively impermeable. It stops the oil and gas from moving through it. Things like shale, dense salt layers, or unfractured limestone often act as seals.
Okay, an impermeable lid.
Exactly. And second, the geometry, the three-dimensional shape of the seal rock and the reservoir rock below it has to create some kind of structural closure, a high point where the buoyant hydrocarbons get concentrated and can't easily escape sideways or upwards past the seal.
So the shape of the rock layers is critical. What kinds of shapes or structures form these traps?
Geologists recognize several common types, formed by different geological processes. The chapter outlines four main ones. First, you have anticline traps.
Anticlines. Those are upward arching folds in the rock layers.
Precisely. They often form when rock layers are compressed, maybe doing mountain building. If you have a sequence with a source rock below, then a reservoir rock, then a seal rock, and the whole package gets folded into an arch or anticline.
The oil and gas would migrate up into the peak of the arch.
Exactly. They move up within the reservoir layer and get trapped at the crest of the fold, right underneath the impermeable seal rock. That's a very common type of trap.
Okay, anticlines. What else?
Second, there are fault traps. Faults are fractures where rocks have moved past each other. Sometimes, the movement along a fault can juxtapose a permeable reservoir rock against an impermeable rock layer, stopping the migration.
So the fault itself acts as a barrier.
It can, yes, or sometimes the fault zone itself gets crushed and ground up, forming a clay-rich, impermeable layer called fault gouge, which can also act as a seal. So faults can create traps in a couple of ways.
Folds and faults. What are the other two types?
Then you have salt dome traps. In some areas, there are thick underground layers of rock salt. Now, salt is actually less dense than most compacted sedimentary rocks like sandstone and shale.
Really? Salt is lighter.
Relatively speaking, yes, especially when buried deep. Over long periods, this lighter salt can slowly flow upwards, pushing through the overlying rock layers and forming these large bulbous structures called salt domes.
Okay.
As the salt pushes up, it bends and breaks the surrounding rock layers. Oil and gas migrating upwards in nearby reservoir rocks can get trapped against the impermeable flanks of this rising salt dome.
Interesting. Salt domes. And the last type?
The last category is stratigraphic traps. These aren't necessarily caused by folding or faulting, but rather by changes in the rock layers themselves related to how they were originally deposited or later eroded.
How does that work?
Well, for example, imagine a tilted layer of sandstone reservoir rock that gradually thins out and disappears. We call that a pinch-out, maybe sandwiched between two impermeable shale layers.
Okay.
Oil and gas migrating up along that sandstone layer will get trapped where the sandstone pinches out because their permeable pathway just ends. Other stratigraphic traps can form where ancient river channels filled with sand are encased in mudstone, or where porous reef limestones are surrounded by impermeable shales.
So these traps are absolutely key for holding onto the oil and gas for us to find. But are they permanent? Like once oil is trapped, is it there forever, geologically speaking?
Not necessarily forever, no. While these traps can hold oil and gas for millions, even hundreds of millions of years, they aren't always perfectly sealed for eternity.
They can leak.
They can. Most rocks, even seals like shale, contain microscopic fractures or larger cracks called joints. Over very long time scales, oil and gas molecules might slowly seep through these imperfections. Also, there are microbes, tiny organisms living deep underground, that can actually consume hydrocarbons as their food source.
Wow, oil-eating microbes.
Yep. So it's quite likely that many oil and gas accumulations that formed in the geological past have since been breached, leaked away, or been biodegraded over vast stretches of time.
It really gives you a sense of the Earth as a dynamic system, constantly changing, even deep underground. Now, the chapter goes into the history a bit, the birth of the conventional oil industry. It wasn't always this massive, high-tech global operation we see today, was it?
Oh, absolutely not. It had very humble and somewhat messy beginnings. People knew about oil seeping out of the ground, rock oil, for thousands of years, using it for things like waterproofing or lubrication.
Even medicine, apparently.
Yes, some questionable patent medicines in the 19th century used it, but it was generally scarce and not a major commodity.
Hmm.
Then in the 1850s, this New York lawyer, George Bissell, had a really forward-thinking idea.
What was that?
He saw that this rock oil could potentially be refined into kerosene to fuel lamps, which could be a much better and cheaper alternative to the whale oil that was becoming increasingly expensive and scarce at the time.
Ah, replacing whale oil? That was a big deal then?
Huge. So Bissell and some investors formed a company. And they hired this fellow, Edwin Drake, often called Colonel Drake, though it was an honorary title, to try something radical. Drilling for oil, specifically near Titusville, Pennsylvania, where oil seeps were known.
The famous Drake well, that's like the origin story of the modern oil industry, right?
It absolutely is. Drake wasn't an oil man. He was a former railroad conductor, but he was persistent. He hired experienced salt well drillers, got a steam engine to power the drill.
Was it easy?
Not at all. It was slow, difficult work. They kept hitting setbacks, and his investors were losing faith, telling him to stop.
Oh, wow.
But on August 27th, 1859, incredibly, the very day he got a letter telling him the funding was cut off, his drillers hit a depth of just over 21 meters, about 70 feet, and oil started filling the borehole.
Amazing timing.
Unbelievable. They quickly rigged up a hand pump and started pumping crude oil out of the ground from a deliberately drilled well for the first time in history. And funny story, they hadn't planned for storage.
So what do?
They just used whatever empty whiskey barrels they could find nearby. And that's why, even today, the standard unit for oil is the barrel, or DBL, equal to 42 U.S. gallons. It literally came from those first whiskey barrels.
That's incredible. And I bet things took off pretty quickly after Drake struck oil.
It exploded is more like it.
Yeah.
Within just a few years, the area around Titusville was just a forest of oil derricks. Hundreds, then thousands popped up. It was a real frenzy.
An oil rush.
Exactly. And by the early 20th century, society was becoming hooked on this stuff. Initially, kerosene for lamps was the main product. But then, as electric lighting started taking over,
Something else came along.
the internal combustion engine and the automobile, suddenly there's this massive new demand for gasoline, another fraction refined from crude oil.
Right.
The early industry was pretty chaotic, boom and bust cycles, fierce competition. That's the environment where John D. Rockefeller built Standard Oil into a near monopoly, controlling almost everything from drilling to refining to sales.
Until it got broken up by the government, right?
Yep. In 1911, the Supreme Court ordered it broken up for being an illegal monopoly. Though, interestingly, some of those pieces have gradually re-emerged over the decades. But the point is, oil quickly became this huge global commodity, deeply tied up with politics, economics, supply, demand, a complex web we still see today.
So the early days were kind of hitting it lucky, finding seeps. How does the modern search for oil work? It must be way more scientific now.
Oh, vastly more sophisticated. You can't just wander around looking for puddles of oil anymore. Most of the easy-to-find stuff is long gone. Modern hydrocarbon exploration is a really complex, high-stakes, and often incredibly expensive business.
Where do they start?
It usually begins with geologists identifying large regions, sedimentary basins that have the right types of rocks. Remember, source rocks, reservoir rocks, seal rocks. They're almost always sedimentary. Then they do extensive field work, mapping the rock layers exposed at the surface, creating detailed geologic maps. From that surface data, they can start building preliminary geological cross-sections, like drawing a slice through the earth, to get an initial idea of how the rock layers might be arranged underground.
But that only tells you so much about what's deep down. How do they see underground? That's where seismic surveys come in, right?
Exactly. That's the crucial next step. Seismic reflection profiling. It's like using sound waves to create an ultrasound image of the Earth's subsurface.
How does that work on land?
On land, they use these special heavy trucks that vibrate the ground, or sometimes carefully controlled dynamite charges, to send seismic waves, sound waves, down into the Earth.
Okay.
When these waves hit a boundary between different rock layers, say sandstone meeting shale, some of the wave energy reflects back up to the surface, like an echo.
And they listen for the echoes.
Precisely. They lay out arrays of sensitive detectors, called seismometers or geophones, on the ground to record the arrival times and the strength of these reflected waves. By analyzing how long it takes the waves to travel down and back and how the waves change, geologists can figure out the depth, thickness, and even some properties of the different rock layers.
And that builds the picture.
Yes, sophisticated computer processing turns all that data into detailed 2D images, or even 3D blocks showing the subsurface geological structures, folds, faults, potential traps. It helps them pinpoint where to drill, or maybe more importantly, where not to drill.
A high-tech treasure map, basically. And they do this offshore, too, under the ocean.
Yep, similar principle, different tools. Instead of vibrating trucks, ships tow devices called air guns. These release powerful bubbles of compressed air into the water, creating seismic waves that travel down through the water and into the rock beneath the seafloor.
Okay.
The reflections from the rock layers bounce back up and are detected by long cables towed behind the ship, studded with underwater microphones called hydrophones.
Same idea, just using air pulses and hydrophones.
Right. And again, complex computer processing creates those detailed images of the subsurface geology beneath the ocean floor, looking for those potential traps. Modern 3D seismic surveys are incredible. They give you this amazing volumetric picture of the underground layers. They cost a fortune, tens of millions of dollars sometimes.
Wow.
But they drastically improve the chances of finding oil or gas and reduce the risk of drilling expensive dry holes.
Okay, so they've done the geology, run the seismic, identified a promising spot that looks like a trap with the right rocks. What's the next step?
Drilling.
Right.
Drilling the exploratory well, yes, and that's a huge decision, a major investment. A deep well can easily cost tens of millions, sometimes hundreds of millions of dollars, especially offshore.
So how does the drilling actually work?
They bring in a drilling rig. Modern rigs use rotary drilling. You have a long string of connected steel pipes, the drill pipe that's rotated from the surface. The bottom end is the drill bit, made of super hard materials that grinds and cuts through the rock. As the bit cuts the rock, they pump a special fluid called drilling mud down to the inside of the drill pipe. This mud serves several critical purposes.
Like what?
Well, it cools and lubricates the drill bit, which gets incredibly hot from friction. It carries the crushed rock cuttings back up the hole to the surface, cleaning the borehole, and very importantly, the weight and density of the mud column exerts pressure downwards.
Why is that pressure important?
It counteracts the natural pressure of any fluids, oil, gas, water, trapped in the rock formations down there. This prevents those fluids from rushing uncontrollably up the wellbore, which could cause a dangerous blowout.
Ah, safety. Got it. So they drill down to the target depth. Then what?
Once they reach the target, they have to complete the well. This usually involves lowering a steel pipe, called casing, into the hole and cementing it in place. This reinforces the borehole and isolates different rock layers from each other. Then they install equipment at the surface, the wellhead, to control the flow if they do find hydrocarbons.
I've seen pictures of old oil fields with wells packed really close together. Is that still how it's done?
Not so much anymore, thanks to huge advances in drilling technology. Early wells were pretty much just vertical holes. So to drain a large underground area, you often needed lots of closely spaced vertical wells.
Right.
But now we have directional drilling, sometimes called deviated drilling. Engineers can actually steer the drill bit underground,
Steer it.
using sophisticated downhole motors and sensors that constantly measure the bit's position and orientation. Combined with adjustments made at the surface, they can drill wells at an angle, even turning them completely horizontal for thousands of feet or kilometers.
Wow, drilling sideways underground.
Exactly. They can follow a specific thin layer of oil-rich shale, for instance, for miles with just one surface well. It's incredibly precise. They can hit targets just a few feet wide from miles away. This drastically reduces the number of wells needed at the surface, minimizing the environmental footprint and making extraction much more efficient.
Okay, so the well is drilled, maybe horizontally encased. How do they actually get the oil and gas out? Does it just flow out on its own?
Sometimes initially, yes. The natural pressure within the reservoir rock might be high enough to push the oil and gas up the well to the surface. That's called primary recovery.
But that doesn't get everything out.
No, typically only a fraction, maybe 10 to 30% of the oil in place. So companies use secondary recovery techniques to get more.
Like what?
A common one is water flooding, injecting water into nearby wells to basically push the remaining oil towards the production wells. For heavier, more viscous oil, they might use steam injection. Pumping high-pressure steam down heats the oil, makes it thinner, less viscous, so it flows more easily.
And what about those really tight rocks, like the shales we talked about?
That's where hydrofracturing or fracking comes in.
Yeah.
That's become a game changer for unconventional resources.
Fracking. We hear that word a lot. How does it work?
Basically, they pump a mixture of water, sand, or tiny ceramic beads called proppants, and some specialized chemicals down the wellbore at extremely high pressure. This pressure creates new tiny fractures in the tight rock formation and props open existing natural fractures.
Creating pathways for the oil and gas.
Exactly. It dramatically increases the permeability of the rock right around the wellbore, allowing the trapped oil and gas to flow out much more readily into the well.
Fracking's definitely controversial, though, isn't it? We'll probably touch on those concerns later. So once the crude oil comes up, what happens to it? It's not usable like that, is it?
No, raw crude oil is a complex mixture of all sorts of different hydrocarbon molecules, often mixed with natural gas and salt water too. First, it goes into separation tanks near the well to separate the oil, gas, and water.
Okay.
Then the crude oil is usually transported pipeline, tanker ship, sometimes truck or train to a refinery.
And what happens at the refinery?
At the refinery, the crude oil is heated up, typically to around 400 degrees Celsius, turning much of it into vapor. This hot mixture is then fed into the bottom of a tall distillation column, sometimes called a fractionating tower.
Distillation, like separating alcohol.
Similar principle, yes, based on boiling points. Inside the column, it's hotter at the bottom and cooler at the top. As the vapor rises, different hydrocarbon components condense back into liquids at different temperatures on trays located at various levels.
So heavier stuff condenses lower down, lighter stuff higher up?
Exactly. The heaviest, longest chain molecules with the highest boiling points, like bitumen for asphalt and heavy fuel oil, condense near the bottom. Then you get lubricating oils, diesel fuel, heating oil, kerosene, then gasoline. And finally, the lightest gases like propane and butane condense or are drawn off near the top.
It's like sorting the molecules by size and boiling point.
Pretty much. Refineries also use processes called cracking, where they use heat, pressure, and catalysts to break down some of those less valuable, larger hydrocarbon molecules into smaller, more valuable ones like gasoline components.
So they can make more gasoline out of the crude.
Correct. And even the really heavy stuff left at the very bottom can be used as feedstock for petrochemical plants to make plastics and other materials.
What about natural gas? Is it always found with oil? How does it compare?
Natural gas is often found alongside oil. It might be dissolved in the oil under pressure or form a gas cap layer above the oil in the reservoir. But you can also have large deposits of natural gas that aren't associated with significant amounts of oil.
And it burns cleaner, right?
Yes, that's a major advantage. When natural gas, which is mostly methane, burns, it produces mainly just carbon dioxide and water vapor. Burning oil, and especially coal, releases a lot more complex pollutants, soot, sulfur compounds, nitrogen oxides, unburned hydrocarbons.
Which is why it's preferred for home heating and cooking.
Exactly. And increasingly for electricity generation, too. Many power plants have switched from coal or oil to natural gas because it's cleaner and, thanks to shale gas, often cheaper now. You can even run vehicles on compressed natural gas.
But sometimes they just burn it off at oil wells. That seems wasteful.
It is wasteful, unfortunately. It's called flaring. In some oil fields, especially smaller or more remote ones, the amount of natural gas produced along with the oil might not be enough to justify the cost of building pipelines or liquefaction facilities to transport and sell it.
So they just flare it, burn it into the atmosphere.
Sadly, yes. It's better than venting raw methane, which is a much more potent greenhouse gas than CO2 in the short term, but it's still a waste of energy and releases CO2. Efforts are underway globally to reduce flaring, but it still happens.
It seems like these conventional oil and gas fields aren't just randomly scattered around the world. Are there specific geological places they tend to show up?
Absolutely. Their occurrence is definitely not random. It's strongly controlled by geological history. Right now, the Middle East, particularly the countries around the Persian Gulf, hold the lion's share of the world's proven conventional oil reserves.
Like how much?
Something like 60% of the global total is concentrated there, mainly in about 25 absolutely enormous fields, giant and supergent fields, each holding billions of barrels.
60%. Why is so much concentrated right there?
It's down to a really unique and fortunate combination of geological factors lining up over millions of years. Back in the Jurassic and Cretaceous periods, that whole region was a shallow, warm, tropical sea.
Ideal for plankton.
Perfect conditions for massive plankton blooms. This led to the deposition of incredibly thick layers of sediments, super rich in organic matter, fantastic source rocks.
Okay, great source rocks.
Then these were buried by thick layers of porous sandstones and fractured limestones, perfect reservoir rocks. And finally, the tectonic collision between the African and Arabian plates with the Eurasian plate squeezed the region.
Creating folds.
Exactly. It created huge anticline folds, which formed perfect traps for all the oil and gas migrating out of those rich source rocks. It was just the perfect geological storm, you might say.
Wow. Where else do we find significant conventional reserves?
Besides the Middle East, other major areas include sedimentary basins along passive continental margins. Think the Gulf Coast of the U.S., offshore Brazil, West Africa. Also, large basins within the stable interiors of continents called intracrotonic basins and foreland basins, which form next to rising mountain ranges like the eastern flank of the Rockies.
Okay, that gives us a good picture of conventional oil and gas. Now let's pivot back to those unconventional reserves. You said they're harder and pricier to extract. What are the main types we should be aware of?
Right, unconventional resources. They hold vast amounts of hydrocarbons, but getting them out is tough, either because the rock has super low permeability or the hydrocarbons themselves are incredibly thick and viscous.
Like that milkshake analogy again.
Exactly. Standard drilling and pumping just doesn't work well. But big advances in technology, especially directional drilling and fracking, combined with periods of higher oil and gas prices, has made tapping into these resources increasingly important globally.
So, what are the big examples of unconventionals being produced now?
Shale gas and shale oil are probably the most prominent right now. Huge quantities of natural gas and oil are trapped within those organic, rich shale source rocks we talked about
The
earlier.
ones that generated the conventional stuff.
Sometimes the very same ones,
Yeah.
yes, or similar ones that never had good migration pathways out. The shale itself might have been heated into the oil or gas window, but it's just so tight, the permeability is so low that the hydrocarbons are stuck there.
Until fracking came along.
Exactly. The combination of drilling long horizontal wells through the shale layer, maximizing contact, and then using multi-stage hydraulic fracturing to create a network of cracks. That's what unlocks it.
Increasing the permeability artificially.
Precisely. It gives the trapped gas and oil pathways to flow into the wellbore. Think of places like the Marcellus Shale in the eastern U.S. or the Bakken Shale in North Dakota. Fracking in these areas has caused a massive boom in U.S. oil and gas production.
But as you mentioned, it's not without controversy.
Definitely not. There's ongoing debate about how much oil and gas can ultimately be recovered, the lifespan of these wells, and of course, significant environmental concerns linked to the fracking process itself.
Right. Let's unpack those environmental concerns around fracking a bit more. What are the main issues people raise?
There are several key ones. A major concern is the potential contamination of groundwater drinking water aquifers, either by the chemical additives used in the fracking fluids or by natural gas or oil migrating upwards from the shale formation through poorly sealed wells or natural fractures.
Is that happening?
Well, the industry generally maintains that fracking itself, happening thousands of feet below aquifers, is unlikely to cause direct contamination, but concerns remain about well integrity, leaky casings near the surface, and the handling of fluids. Methane can also occur naturally in some water wells, so distinguishing natural sources from potential fracking-related contamination is complex.
What else?
Water usage is another big one. Fracking uses enormous volumes of water, which can strain local water resources, especially in dry areas. Then there's the issue of wastewater disposal.
The water that flows back out of the well.
Yes, the flowback and produced water. It contains the original fracking chemicals, plus salts, heavy metals, and sometimes naturally occurring radioactive materials picked up from the deep rock formations. Disposing of this contaminated water safely is a major challenge. Often it's injected deep underground into disposal wells.
And that injection has been linked to earthquakes.
Yes, in some areas, injecting large volumes of wastewater deep underground has been linked to induced seismicity, triggering small and occasionally moderate earthquakes on previously unknown or inactive faults.
Any other concerns?
Increased truck traffic for hauling water and equipment puts a strain on local roads and infrastructure. There are concerns about air pollution from drilling rigs, diesel engines, compressors, and sometimes flaring of gas. And the whole infrastructure needed to transport this new oil and gas pipelines. Rail cars raises its own set of potential risks like leaks, spills, or accidents like the tragic Lac-Mégantic train derailment involving volatile Bakken crude.
So a lot of complex issues to weigh. On the flip side, you mentioned shale gas has led to shifts in electricity generation.
Yes, the increased availability and lower price of natural gas, largely due to shale gas production, has prompted a significant shift away from coal towards natural gas for generating electricity in the U.S. and some other places because gas burns cleaner.
Okay, let's move to another unconventional. Tar sands or oil sands, like the ones up in Canada. How are they different?
Tar sands, or oil sands, are quite different. They're basically deposits of sand or poorly cemented sandstone where the pore spaces are filled with bitumen.
Bitumen.
Bitumen is an extremely thick, viscous, heavy form of oil. Think cold molasses or asphalt. It's way too thick to be pumped out using conventional methods. It just sits there, coating the sand grains.
How did it get like that? Was it always tar?
No, the thinking is that it started out as conventional liquid oil that migrated into these shallow sandstone deposits millions of years ago. But because they were relatively shallow, naturally occurring microbes were able to get in and attack the oil.
The oil-eating microbes again?
Yep. They basically consume the lighter, smaller, more easily digestible hydrocarbon molecules, leaving behind only the really heavy, large, complex, viscous ones, the bitumen. It's called biodegradation.
So how do they get that sticky bitumen out?
It's challenging and very energy intensive.
Okay.
If the tar sands are close to the surface, they use huge open pit mining operations. Giant shovels dig up the sand, load it onto massive trucks.
Mining for oil, essentially.
Pretty much. The mine sand is then taken to processing plants where it's mixed with hot water and chemicals to separate the bitumen from the sand and clay. This bitumen then needs to be upgraded, chemically cracked into smaller molecules to create a synthetic crude oil that can be refined like conventional oil.
And if the tar sands are too deep to mine?
Then they use in situ methods, meaning in place. They drill wells and inject high-pressure steam, or sometimes solvents, down into the tar sand formation. This heats the bitumen, makes it less viscous, allowing it to slowly flow towards other wells where it can be pumped to the surface.
Both methods sound like they'd have a pretty big environmental footprint.
They do. The mining operations involve massive landscape disturbance and create huge tailings ponds to hold the wastewater. Both mining and in situ methods use large amounts of energy, often natural gas to generate steam, and water, and have significant greenhouse gas emissions associated with extraction and processing.
Okay, now oil shale. That sounds similar to shale oil, but the chapter says it's different. The names are confusing.
They are very confusing and often used interchangeably in popular discussion, which doesn't help. But geologically speaking, they are distinct. Oil shale is the rock. It's an organic-rich shale that contains a large amount of solid kerogen.
A precursor stuff we talked about earlier?
Exactly. It's a source rock that never got buried deep enough or hot enough for long enough to naturally cook that kerogen into liquid oil. So, oil shale contains solid organic matter. Shale oil, on the other hand, usually refers to the actual liquid oil that is trapped within the tiny pores of a low permeability shale formation, the stuff extracted by fracking.
So oil shale has the ingredients. Shale oil is the oil in tight rock. Got it.
Right. And oil shale is also different from coal. Coal is mostly carbon from plants. Oil shale is waxy hydrocarbon precursors, kerogen. Interestingly, you can actually burn some high-grade oil shale directly as a fuel, though it's low quality.
But can you get liquid oil out of oil shale?
Yes, but it requires processing. Usually, it involves mining the oil shale, crushing it, and then heating it to very high temperatures, around 500 degrees Celsius, in a vessel called a retort. This artificial heating breaks down the kerogen and releases a liquid hydrocarbon product, sometimes called shale oil in this context, adding to the confusion, or synthetic crude.
Where do we find large oil shale deposits?
There are huge deposits around the world. Estonia, Scotland, China, Russia have significant ones. And the Green River Formation in the western U.S., Wyoming, Colorado, Utah holds absolutely enormous quantities of kerogen.
So why aren't we using it more if there's so much?
Primarily cost and environmental issues. Mining and retorting oil shale is expensive, energy intensive. You need to input a lot of energy to get energy out, uses significant amounts of water, and leaves behind large volumes of spent shale waste that needs to be disposed of. It hasn't been widely economical compared to conventional oil or even fracked shale oil, though technology continues to evolve.
Okay, one last unconventional mentioned is gas hydrate, methane trapped in ice. That sounds pretty wild.
It is pretty wild. Gas hydrate, often specifically methane hydrate, is this solid, ice-like substance. It's basically methane molecules trapped inside a cage-like structure formed by frozen water molecules.
Like methane prisoners in an ice cage.
That's a good way to picture it. It looks like white ice, but if you light it, the escaping methane will actually burn.
Where does this stuff form?
It forms under specific conditions of low temperature and high pressure. You find it mainly in sediments beneath the deep ocean floor on continental slopes and rises, and also within permafrost regions on land in the Arctic.
How does the methane get there?
The methane itself is mostly produced by microbes, anaerobic bacteria breaking down organic matter buried in the sediments. If this methane encounters cold water under high pressure, it can get trapped in these hydrate structures.
And is there a lot of it?
Potentially, yes. Geological estimates suggest the total amount of methane locked up in gas hydrates globally could be immense, possibly more energy than all other known fossil fuels, oil, gas, coal combined.
Wow. So why aren't we tapping into this huge resource?
Several major challenges. First, we don't currently have safe, reliable, and economically viable technologies to extract methane from hydrates on a large scale, especially from deep ocean sediments. Second, there are significant environmental risks.
Like what?
Well, methane is a potent greenhouse gas, much more powerful than CO2 over shorter timescales. If mining or warming oceans destabilize these hydrates, large amounts of methane could be released into the atmosphere, potentially accelerating climate change. Also, destabilizing hydrates on the seafloor could trigger large underwater landslides, which could potentially generate tsunamis. So it's a huge potential resource, but the technical hurdles and environmental risks are very significant and still being researched.
Okay, so a lot of potential in unconventionals, but also significant challenges, technical, economic, and environmental. Let's switch gears now to the other major fossil fuel, coal. It comes from plants, not plankton, right? A totally different origin story.
Completely different origin, yes. Coal is a black or brownish-black, brittle sedimentary rock. Unlike oil and gas, which are fluids made of hydrocarbons, coal is mostly composed of elemental carbon, along with some other organic bits and inorganic impurities like clay or quartz.
But it's still a fossil fuel, stored energy from the past.
Absolutely. It's stored solar energy captured by plants through photosynthesis millions of years ago. But the starting material isn't plankton lipids. It's terrestrial plant matter, wood, leaves, roots, stems that accumulated in swamps.
So you needed land plants first.
Exactly. Significant coal deposits could only start forming after vascular land plants evolved, which was around the late Silurian period over 400 million years ago. The really massive coal deposits we mine today mostly formed during two later periods. The Carboniferous,
Carboniferous name for carbon makes sense.
precisely, and the Cretaceous period. Both of these times had widespread warm, humid climates that were ideal for lush plant growth in swampy environments.
Coal swamps, I've heard that term. What were those ancient environments like? How did they lead to coal?
Imagine vast, low-lying wetlands, maybe like the Everglades or parts of the Amazon basin today, but covering huge areas of continents. These were the coal swamps, densely vegetated, waterlogged areas. The key thing was the waterlogged, stagnant conditions. When plants died, they fell into this water, which was often oxygen-poor or anoxic, just like the seafloor conditions needed for oil-source rocks.
Lack of oxygen again to prevent decomposition.
Exactly. Without enough oxygen, the normal bacteria and fungi that break down dead wood couldn't do their job completely. So instead of fully decomposing, the plant debris just piled up layer upon layer, forming this thick, spongy, partially decayed mass called peat. You can still find peat forming today in bogs and swamps.
So peat is the first step.
Peat is the precursor material, yes. It's maybe 50% carbon. To turn into coal, this peat needs to be buried.
How does that happen?
Over time, the swamp environment might shift or sea levels might change. Rivers might deposit layers of sand and mud over the peat bog, or the sea might advance and lay down marine sediments. This burial under layers of sediment is crucial.
Why burial? What does that do?
Two things: pressure and heat. As the peat gets buried deeper and deeper, sometimes several kilometers down in subsiding sedimentary basins, the weight of the overlying sediments squeezes out water and compacts the peat.
Okay.
And just like with oil formation, the deeper it gets buried, the hotter it gets due to the geothermal gradient. This combination of pressure and heat over millions of years drives slow chemical and physical changes. Volatile compounds, things like water, CO2, methane, are driven off, leaving behind material that's increasingly concentrated in carbon.
And that's coal.
Once the carbon content gets above about 60%, we officially call it coal. And the deeper the burial and the higher the temperature it reaches, the higher the rank or quality of the coal.
Right. The chapter talks about different ranks: lignite, bituminous, anthracite. What's the difference?
It's basically a progression based on how much heat and pressure the peat experienced.
Yeah.
Lignite is the lowest rank. It's often brownish, relatively soft, has high moisture content, and maybe 60–70% carbon. It forms under relatively low temperatures, less than 100 degrees C. If it gets buried deeper and heated more, between about 100 and 200 degrees C, lignite transforms into bituminous coal. This is the most common type mined globally. It's blacker, harder, has less moisture, and a higher carbon content, maybe 70–85%. It's the main coal used for electricity generation and steelmaking.
And anthracite is the highest rank.
Yes, andesite is the top grade. It's very hard. Shiny black has the highest carbon content, over 85%, and the lowest moisture and volatiles. It burns very hot and cleanly. It forms at higher temperatures, say 200 to 300 degrees C.
Where do you typically find anthracite?
You often find it in regions that have experienced significant geological squeezing and heating, like along the edges of mountain belts where rocks have been deeply buried and heated by tectonic forces or hot fluids. If you heat it even more, beyond coal rank, you eventually just get graphite, so you don't find coal in highly metamorphosed rocks.
Like oil and gas, coal is found in sedimentary layers. How do geologists look for it?
Since coal comes from ancient swamps, geologists look for sedimentary rock sequences that formed in those kinds of environments. Think tropical to subtropical coastal plains, river deltas, non-marine basins from the Carboniferous or Cretaceous periods primarily.
Okay.
They use geological mapping to identify these potentially coal-bearing formations. Then they drill core samples to see if coal seams are actually present, how thick they are, how deep they are, and what the quality or rank is. Seismic surveys can also help map out the structure of the coal beds underground.
Where are the biggest coal reserves found around the world?
Yeah.
And who's using the most coal today?
The largest estimated recoverable reserves are actually in the United States, followed by Russia, Australia, China, and India. But in terms of who's using the most coal, it's overwhelmingly the Asia-Pacific region. They account for something like 70% of global consumption. China became the world's largest consumer back in the 1980s, surpassing the U.S., and its consumption grew massively in the early 2000s with its industrial boom. However, global coal use seems to have plateaued or maybe even started to decline slightly in recent years. In the U.S., for example, there's been a big shift towards natural gas and renewables for electricity.
So once they find a good coal seam, how do they get it out? We see pictures of those huge open pit mines, but also underground mines.
Right. The method depends mainly on the depth of the coal.
Yeah.
If the seam is relatively shallow, say within 100 meters or about 330 feet of the surface, strip mining or surface mining is usually the most economical way.
How does that work?
They use enormous machines like giant dragline excavators to literally strip away the overlying soil and rock, which they call overburden. Once the coal seam is exposed, smaller equipment like bulldozers and loaders dig out the coal.
That sounds like it could cause a lot of surface disruption.
Historically, it did, leaving big scars on the landscape and sometimes causing acid mine drainage when sulfur minerals in the waste rock were exposed to air and water. Modern regulations in many places now require reclamation, putting the overburden back, recontouring the land, replacing topsoil, and replanting vegetation. But it's still a major disturbance.
What about in hilly areas?
In mountainous regions like Appalachia, a controversial method called mountaintop removal is sometimes used. They literally blast the top off a mountain to get at the coal seams beneath and dump the waste rock into adjacent valleys. It's very destructive environmentally.
And for deeper coal seams?
For deeper seams, they have to go underground. They sink vertical shafts or drive sloping tunnels down to the coal seam, then create a network of tunnels within the seam using specialized mining machines that grind away the coal.
Like continuous miners.
Exactly, or longwall mining systems. They have to manage roof support, ventilation, and transport the coal back to the surface.
Underground mining sounds pretty dangerous.
It has historically been very dangerous, yes. Roof collapses are a major risk. Methane gas, which is naturally present in coal seams, is highly explosive, so ventilation is critical to prevent explosions.
And the dust.
Coal dust is another huge hazard. Breathing in fine coal dust over long periods causes coal workers pneumoconiosis, or black lung disease, which is debilitating and incurable. Safety has improved dramatically with modern technology and regulations, but it remains a challenging environment.
The chapter also mentions getting gas from coal itself, not just finding natural gas nearby. How does that work?
Right, there are two main ways. One is coal bed methane. Natural gas, mostly methane, is actually generated during the coal formation process and gets trapped within the coal structure itself, absorbed onto the coal molecules or in tiny pores and fractures called cliques.
So you can drill for gas in the coal seam?
Yes. For deep coal seams that are too deep to mine, they can drill wells into them and pump out the groundwater that fills the cleats. Lowering the water pressure allows the trapped methane to desorb from the coal and flow to the well where it can be collected. One challenge is managing the large volumes of water that get pumped out, which can be salty.
And the other way, gasification.
Coal gasification is a different process. It's a technology to convert solid coal into a mixture of combustible gases, hydrogen, carbon monoxide, some methane, often called syngas, or synthetic gas.
How do they do that?
They react pulverized coal with steam and oxygen under high pressure and temperature. This breaks down the coal structure and produces the syngas. An advantage is that you can remove impurities like sulfur and mercury from the syngas before burning it, making it a cleaner fuel than burning raw coal directly. This syngas can then be burned in turbines to generate electricity or used to synthesize other chemicals or liquid fuels.
Finally, on coal, the chapter mentions underground coal fires. That sounds pretty bad.
It's a really serious and persistent problem in many coal regions. Coal seams, once exposed to oxygen, can actually ignite and burn underground.
How do they start?
Lots of ways: lightning strikes, spontaneous combustion, coal can slowly oxidize and heat up on its own if exposed to air, methane explosions in mines, even careless things like trash fires set in abandoned mine pits.
And they're hard to put out.
Incredibly difficult, often impossible. They can smolder underground for decades, even centuries, slowly consuming the coal seam. They draw oxygen through cracks in old mine workings. They produce toxic gases, cause the ground surface to collapse, pollute groundwater, and release a lot of greenhouse gases. The fire in Centralia, Pennsylvania, that's been burning since 1962 and forced the town to be abandoned is a famous example. But there are thousands burning worldwide, especially in places like northern China.
Wow, a sobering legacy of mining in some places. Okay, let's shift gears completely now. Let's talk about nuclear power. This is a fundamentally different way of getting energy than burning fossil fuels, right?
Totally different process, yes. Fossil fuels release energy through chemical reactions, rearranging electrons and atoms. Nuclear power releases energy from changes within the nucleus of an atom through nuclear fission.
Fission, splitting the atom.
Exactly. Specifically splitting the nucleus of certain heavy, unstable atoms, like a particular type of uranium, uranium-235. When the nucleus splits, it releases an enormous amount of energy that was holding the nucleus together. Think Einstein's ENC4, plus it releases neutrons.
And those neutrons cause more splitting.
Precisely. Those released neutrons can then hit other nearby uranium-235 nuclei, causing them to split, releasing more energy and more neutrons, creating a self-sustaining chain reaction.
How do they harness that energy in a power plant?
The heart of the plant is the reactor core. It contains the nuclear fuel, usually pellets of uranium oxide, packed into long metal fuel rods. The chain reaction is allowed to proceed in a controlled way within these rods, generating a tremendous amount of heat.
Controlled being the key word there.
Absolutely critical. They use control rods, made of materials that absorb neutrons, like cadmium or boron, which can be moved in or out of the core to speed up or slow down the chain reaction and keep it stable.
So the heat is generated. How does that make electricity?
The heat from the fission process is used to heat water flowing through or around the reactor core. This superheated water, often kept under high pressure so it doesn't boil in the primary loop, then goes to a heat exchanger, where it boils water in a separate secondary loop, creating high-pressure steam.
Ah, and the steam drives a turbine, like in a coal or gas plant.
Exactly the same principle from there on. The steam spins a turbine, the turbine spins a generator, and the generator produces electricity. The steam is then condensed back into water, often using those big cooling towers you see, and cycled back to be heated again.
Nuclear fuel is famous for being incredibly energy dense, right?
Phenomenally so.
Yeah.
A small pellet of uranium fuel, maybe the size of your fingertip, can release as much energy as a ton of coal or hundreds of gallons of oil. That's a huge advantage. Plus, the fission process itself doesn't produce greenhouse gases or the kind of air pollutants that fossil fuels do.
So high energy density, no direct air pollution or CO2. Sounds great, but obviously there are concerns.
Yes, despite those advantages, nuclear power faces significant public and societal concerns, primarily around safety, the risk of accidents, and the long-term management of the radioactive waste produced. Still, some countries, like France historically and China more recently, rely heavily on or are expanding nuclear power to reduce fossil fuel dependence and air pollution.
Where does the uranium fuel actually come from? Is it mined, like coal?
Yes, uranium is mined. It's an element that was present when the Earth formed, probably created in ancient supernova explosions. Geochemically, uranium atoms are kind of large and awkward. They don't fit easily into the crystal structures of most common minerals that form deep in the Earth.
So they get concentrated elsewhere.
Exactly. When rocks melt deep underground, the uranium tends to stay in the liquid magma. As that magma rises and cools to form rocks like granite near the surface, the uranium gets concentrated in the last bits of magma to solidify, or in fluids associated with it.
So granite can be slightly radioactive?
Generally, yes, slightly more than other rocks. But to get mineable concentrations, you need further geological processes. Hot water circulating through granite can dissolve the uranium and then reprecipitate it in concentrated veins, often as the mineral pitch blende.
Okay.
Another way is through weathering and erosion. Uranium minerals can get concentrated in ancient river gravels like gold panning, but for uranium. Or groundwater flowing through uranium-bearing rocks can dissolve the uranium, carry it along, and then precipitate it when the water chemistry changes, often concentrating it in porous sandstones.
And the uranium they mine, is that directly usable as fuel?
Not usually in the most common reactor types. Natural uranium is mostly uranium-238, which doesn't fission easily. Only about 0.7% is the fissionable isotope, uranium-235.
So they need more U-235.
Right. For most reactors, the uranium fuel needs to be enriched. The concentration of U-235 has to be increased, typically to about 3 to 5%. This enrichment process is complex and energy-intensive.
Okay, let's talk about the challenges. Safety is obviously paramount. What are the main risks in operating a nuclear plant?
The biggest risk is losing control of the heat generated by the fission process. Even after you shut down the chain reaction, the radioactive decay of the fission products continues to generate significant heat for a long time. You absolutely need reliable cooling systems to continuously remove this decay heat.
What happens if the cooling fails?
If cooling is lost, the fuel rods can overheat and melt. That's a meltdown. The molten fuel could potentially melt through the reactor vessel. At extremely high temperatures, the metal cladding of the fuel rods can react with water or steam to produce hydrogen gas.
Hydrogen gas, that's explosive, right?
But highly explosive. A hydrogen explosion inside the containment building could potentially damage it and allow radioactive materials to escape into the environment. That's a major accident scenario.
Is a meltdown like an atomic bomb?
No, absolutely not. That's a common misconception. An atomic bomb requires highly enriched uranium, like 90% U-235, brought together very rapidly to create a supercritical mass and an uncontrolled instantaneous chain reaction. Reactor fuel is much less enriched, and the core geometry isn't designed for that. A meltdown is a release of radiation due to overheating and potential containment breach, not a nuclear explosion.
Unfortunately, there have been some serious accidents. The chapter mentions the big ones.
Yes, 3 stand out. 3 Mile Island in Pennsylvania in 1979 involved a partial meltdown due to loss of coolant caused by mechanical failures and human error. But the containment building largely held, and radiation release was limited.
Okay.
Chernobyl in Ukraine in 1986 was much, much worse. A flawed reactor design combined with operators disabling safety systems during a test led to a power surge, steam explosions, and a graphite fire that completely destroyed the reactor and released massive amounts of radiation over a huge area.
Devastating.
Truly. And then Fukushima Daiichi in Japan in 2011, a massive earthquake triggered a huge tsunami that overwhelmed the plant's seawalls and knocked out both primary and backup power needed for cooling. This led to meltdowns in 3 reactors and hydrogen explosions that damaged the buildings and released significant radiation, mostly into the ocean but also into the air.
These accidents really highlight the potential consequences if things go wrong.
They absolutely do. They've led to major reviews of safety procedures, reactor designs, and emergency preparedness worldwide.
And the other huge challenge is waste. What do we do with the spent nuclear fuel? It stays radioactive for a really long time, doesn't it?
For an incredibly long time, yes. Spent fuel rods contain unused uranium, plutonium created during fission, and a whole cocktail of highly radioactive fission products. Some of these isotopes remain hazardous for tens or hundreds of thousands of years.
So you can't just throw it away?
Absolutely not. It needs to be isolated from the environment for millennia. The internationally preferred solution is deep geological disposal, sealing the waste in robust containers, and burying it hundreds of meters down in stable rock formations, far from groundwater.
But finding a place to do that is hard.
Extremely difficult, politically and socially. Nobody wants a long-term nuclear waste repository in their backyard. The Yucca Mountain project in Nevada, which was studied for decades in the U.S., ultimately stalled due to political opposition.
So where does the waste go now?
Currently, in most countries, spent fuel is stored on-site at the power plants, initially in large pools of water for cooling, and later transferred to dry storage casks, large concrete and steel containers. This is considered a safe interim solution, but it's not a permanent fix. Finding a permanent disposal solution remains a major unresolved issue for the nuclear industry globally.
So nuclear offers zero carbon power, but safety and waste are huge, persistent challenges. Okay, let's broaden out now to the other energy sources. The chapter covers the renewables and alternatives beyond fossil fuels and nuclear.
Right. This is where we look at sources like geothermal, biofuels, hydro, wind, and solar.
Let's start with geothermal. harnessing Earth's internal heat.
Exactly. Earth's interior is hot, and in some places that heat comes closer to the surface. We can distinguish between high-temperature geothermal, used for commercial power generation, and low-temperature or ambient geothermal for heating and cooling buildings.
How does the high-temperature stuff work for electricity?
In volcanically active regions, or areas with thin crust or high heat flow, groundwater circulating deep underground can get heated to very high temperatures, sometimes turning into steam. Companies drill wells to tap into this hot water or steam.
And use it to drive turbines.
Precisely. The steam directly, or steam flashed from the hot water, drives turbines connected to generators. Places like Iceland, New Zealand, parts of California, and Italy make significant use of high-temperature geothermal power.
And the low-temperature kind. For homes.
That uses the fact that the ground just a few meters down stays at a relatively constant temperature year-round, warmer than the air in winter, cooler in summer. Geothermal heat pumps circulate a fluid through underground pipes to exchange heat with the ground, making home heating and air conditioning much more efficient. It doesn't generate electricity, but it significantly reduces the energy needed for heating and cooling.
Okay, what about biofuels, making fuel from plants?
Yes, biofuels are derived from biomass, recently living organic matter. The most common is ethanol, an alcohol fuel.
Usually made from corn in the U.S.?
Mostly corn in the U.S., yes. They ferment the corn sugars into ethanol. In Brazil, they use sugarcane very effectively. There's also a lot of research into making ethanol from non-food sources like switchgrass or wood chips, cellulosic ethanol, or even from algae.
And biodiesel.
Biodiesel is made from vegetable oils like soybean or canola oil, or animal fats, through a chemical process. It can often be used in standard diesel engines with little or no modification.
Then there's hydropower and wind power. We've used those in simpler forms for ages, right? Water wheels and windmills.
Absolutely. Modern hydroelectric power uses dams to create reservoirs. The water falling from the reservoir through pipes, penstocks, spins turbines connected to generators. It's a major source of renewable electricity globally. Think Hoover Dam or the Three Gorges Dam in China.
But dams have environmental impacts too.
Significant ones, yes. They flood large areas, displace people and wildlife, alter river ecosystems downstream, block fish migration, and trap sediment that would normally replenish deltas. Tidal power is another form, using barrages or underwater turbines to harness the energy of ocean tides.
And wind power, those giant turbines we see now.
Modern wind turbines are essentially sophisticated windmills designed to generate electricity. Wind farms group many turbines together in windy locations, onshore or increasingly offshore. The wind spins the large blades, which turn a generator.
Advantages and disadvantages.
Clean energy, no emissions during operation. But wind is intermittent, requires windy locations. Some people object to their visual impact or noise, and there are concerns about bird and bat mortality and potential impacts on marine life for offshore farms.
What about harnessing the sun directly? Solar energy.
The sun is our ultimate energy source, bathing the earth in vast amounts of energy. We can capture it in a couple of main ways for electricity.
Yeah.
One way is concentrated solar power, or CSP. This uses mirrors, sometimes huge fields of them, to focus sunlight onto a receiver, heating a fluid to produce steam that drives a turbine, just like geothermal or nuclear.
Okay.
The other, much more common way now, is photovoltaics, or PV solar panels. These use semiconductor materials, usually silicon, that directly convert sunlight into electricity through the photovoltaic effect. When photons from sunlight hit the silicon atoms, they knock electrons loose, creating an electric current.
And the cost of solar panels has come down a lot.
Dramatically. That's why you see them proliferating on rooftops and in large solar farms all over the world. It's becoming one of the cheapest ways to generate new electricity in many places. Storage is still a challenge for when the sun isn't shining, though.
Lastly, the chapter mentions fuel cells. How do they fit in?
Fuel cells are like batteries that you continuously feed fuel to. They generate electricity through a direct chemical reaction, not combustion. The most common type is a hydrogen fuel cell.
How does that work?
Hydrogen gas is fed to one electrode, the anode, oxygen from the air to the other, the cathode. Electrolyte material in between allows protons, from splitting the hydrogen, to pass through, but forces the electrons to go through an external circuit, creating electricity. The protons, electrons, and oxygen then combine at the cathode to form water.
So the only emission is water.
If you use pure hydrogen, yes. They're very efficient and clean at the point of use. The big challenges are producing the hydrogen fuel efficiently and cleanly, often requires energy itself, and storing and transporting hydrogen safely and affordably.
Okay, so a whole range of alternatives, each with promise, but also hurdles. Now, the final section of the chapter really pulls back to look at the big picture. Energy choices, energy problems. It talks about the age of oil. Are we still in it?
Largely, yes. Oil became the dominant global energy source in the mid-20th century and still holds the largest share of the world's primary energy consumption, though its dominance is maybe starting to wane slightly.
Has consumption changed?
In many industrialized countries, oil consumption has leveled off or even decreased a bit due to efficiency gains and switching to other fuels. But demand is still rising significantly in rapidly developing economies in Asia, South America, the Middle East. The U.S. and China remain the world's biggest consumers overall.
Oil prices have been a roller coaster over the past few decades. What drives that volatility?
It's a complex mix. Geopolitics in major producing regions plays a huge role. Wars, revolutions, political instability can disrupt supply or create uncertainty. Global economic conditions are key. Demand rises during booms, falls during recessions, refinery capacity matters, and increasingly the cost and availability of new technologies, like fracking for unconventional oil, influence supply. Even market speculation can affect short-term prices. It wasn't always like this. Prices were fairly stable until the OPEC actions in the 1970s really shook things up.
And those price swings affect whether unconventional sources are viable.
Absolutely. High prices make expensive methods like deepwater drilling or tar sands extraction profitable. Low prices can shut those projects down.
The really big question, though, how much conventional oil is left? When will it run out? The chapter brings up Hubbert's peak.
Right, and King Hubbert was a geologist who, back in the 1950s, predicted that oil production from any finite resource, whether a single field or a whole country, would follow a bell-shaped curve rise, reach a maximum peak, and then inevitably decline.
And he predicted the U.S. peak.
He did, remarkably accurately, predicting the peak for the lower 48 U.S. states would happen around 1970, which it did. Applying the concept globally is trickier, because new discoveries and technologies keep changing the picture. But the fundamental point remains. Conventional oil is finite.
So have we reached the global peak yet?
That's fiercely debated among experts. Some argue the global peak for conventional crude oil production may have already occurred sometime in the 2000s or early 2010s. Others think it's still a few years away, or that unconventional oil will push the overall liquids peak further out. But pretty much everyone agrees that the rate of discovering new giant conventional fields has fallen way behind our rate of consumption for decades now. We're finding less than we're using.
So what does that mean long term? How long might supplies last?
If you look at estimates of remaining proven conventional reserves, plus estimates of what might still be discovered, and divide by current consumption rates, you generally get figures suggesting maybe 50 to 100 years left for conventional oil.
Not that long in the grand scheme of things.
Yeah, it really isn't. So society faces some stark choices. We can try to drastically reduce consumption through efficiency and conservation. We can rely more heavily on unconventional supplies like shale oil and tar sands, which are more abundant but have higher costs and environmental impacts. Or we can accelerate the transition to alternative renewable energy sources.
Will we really use every last drop?
Probably not. Even the unconventional resources, while vast, are finite. Adding them in might extend the age of oil to maybe a few hundred years total, but that's still just a blip in human history. More likely, a combination of rising extraction costs for the harder-to-get stuff, growing environmental concerns, and the falling costs of alternatives will drive a transition away from oil well before it's completely physically exhausted.
Speaking of environmental concerns, the chapter really emphasizes that using fossil fuels has major consequences beyond just running out.
Absolutely. The entire life cycle, finding, extracting, transporting, and burning them, has significant environmental impacts.
Like what during extraction?
Drilling oil and gas wells requires clearing land, building roads, potentially disrupting habitats. There's always the risk of accidents, like blowouts, uncontrolled gushers of oil and gas, which can cause fires and pollution. Offshore blowouts, like the Deepwater Horizon disaster in the Gulf of Mexico in 2010, can be particularly catastrophic, releasing huge amounts of oil into sensitive marine environments.
And transportation, spills.
Oil spills from pipelines, tankers, even rail cars are a constant risk. Spills on land can contaminate soil and groundwater. Spills at sea create slicks that harm marine life, seabirds, and coastal ecosystems.
What about coal mining impacts?
Surface mining, as we discussed, causes major landscape disturbance, habitat loss, and can lead to acid mine drainage polluting streams for decades, even after mining stops. Mountaintop removal is particularly destructive. Underground mining also risks generating acid drainage that can get into groundwater and can lead to land subsidence if the mine collapses later.
And then there's the air pollution from actually burning them.
Right. Burning fossil fuels releases a whole host of pollutants. Soot, particulate matter, carbon monoxide, sulfur dioxide, SO2, nitrogen oxides, oxotics, unburned hydrocarbons, mercury, especially from coal. These cause smog respiratory problems.
And acid rain.
Yes, SO2 and NOx react in the atmosphere to form sulfuric and nitric acids, which fall back to Earth as acid rain, damaging forests, lakes, and even buildings.
And the biggest one these days, greenhouse gases.
Exactly. Burning any fossil fuel releases carbon dioxide, CO2, the primary greenhouse gas driving climate change. The buildup of CO2 and other greenhouse gases in the atmosphere traps heat, leading to global warming, rising sea levels, changing weather patterns, ocean acidification, and a whole cascade of impacts on ecosystems and human societies. The chapter really highlights the Deepwater Horizon spill as a case study of just how badly things can go wrong with fossil fuel extraction.
And the chapter also circles back to remind us that the alternatives aren't perfect either, right?
That's a crucial point for balance. Every energy source has some trade-offs. Nuclear has the waste and safety concerns. Large hydro dams have major ecosystem impacts. Geothermal is geographically limited for large-scale power. Wind and solar are intermittent and have land use or visual impacts. Biofuels can compete with food production or require significant land and water.
So there's no single silver bullet.
Not really. The future likely involves a diverse mix of energy sources, coupled with significant improvements in energy efficiency and potentially new technologies we haven't even fully developed yet.
Well, this has been an incredibly thorough journey through the world of energy resources. We've gone from the microscopic plankton origins of oil to the immense heat of nuclear fission, the ancient swamps of coal formation, and the potential of harnessing the sun, wind, and Earth's heat. That chapter title, Squeezing Power from a Stone, really does feel apt after covering all this.
It does, doesn't it? We've covered the geology behind where these resources form, how we find and extract them, both conventional and unconventional, the science of nuclear power, and the pros and cons of the various alternatives. And the core message that comes through is that our reliance on fossil fuels, particularly oil, is based on finite resources formed over millions of years that we're consuming in just a couple of centuries.
Yeah.
Understanding the geology, the limits, and the consequences, environmental and otherwise, is just so critical as we navigate the energy transition that has to happen.
Yeah.
The age of oil was transformative, but as the chapter makes clear, it's inevitably a temporary phase in human history.
So, thinking about all this, the finite nature of fossil fuels, the environmental costs, the challenges with alternatives, what single energy source do you think holds the most promise for a truly sustainable future? And what are the biggest hurdles, technological, societal, we need to overcome to get there? Or maybe, looking back from the future, how will people thousands of years from now view our current era of burning through millions of years of stored sunlight in just a few generations? Definitely some big questions to ponder.
Big questions indeed. And just to confirm for you listening, we have worked our way through all the key sections and core concepts from that chapter in Earth, Portrait of a Planet. We've hit the geology, the processes like hydrocarbon generation and coal formation, touched on the ideas illustrated in the diagrams, mentioned specific examples like the Lamesa oil field or New Zealand's geothermal plants when they came up, and discussed the practical applications like drilling and fracking, all as presented in the source material.